Okay, good morning everyone. Let me introduce myself. My name is Sebastián Nery-Cepeda, and in collaboration with Karla, Lucia, Pinales-Muñiz, Braulio, Canales-Pradis, and PhD Sergio, Enrique, Díaz-Silvestre, I present to you the project we have been working on, which is titled Turmeric Nanoparticles with Beta-Glucane and Vitamin C, D3, and Zinc. Okay, here we have the presentation content. And then, malnutrition in Mexico is a public health issue affecting a significant portion of the population due to factors such as poverty, lack of access to healthy foods, and insufficient knowledge about balanced diet. This context has driven a growing demand for nutritional products that are not only beneficial for health but also appetizing, novel, and cost-effective. Within this scope, natural dietary supplements have gained considerable relevance. These products, designed to complement the daily diet, contain ingredients that provide essential nutrients such as vitamins, minerals, amino acids, and other bioactive compounds that may not be present in sufficient quantities in everyday food. In this context, nanotechnology has emerged as a key tool in the evolution of dietary supplements and the food industry in general. The application of nanotechnology enables the creation of more efficient and targeted products, improvising the absorption effectiveness of nutrients in the human body. Recent studies have supported the use of turmeric nanoparticles as a safe material for both biomedical and nutritional application due to their optimal biological properties such as biocompatibility, biodegradability, and no cytotoxicity. Therefore, the present project aims to synthesize turmeric nanoparticles loaded with beta-glucane and vitamin C, D3, and zinc to evaluate their use in dietary supplements.
Continue with the methodology. The methodology used in this work is based on the studies report by Gomez in 2018 and Lee in 2016. The process employed of the synthesis of turmeric nanoparticles encapsulated in beta-glucan with the addition of vitamins C, D3, and zinc. Using the chemical precipitation method is described below. Initially, two precursor solutions were prepared. The first solution was obtained by adding 10 milligrams of commercial turmeric to 100 milliliters of ethanol. This mixture was stirred constantly at 120 rpm at room temperature for 60 minutes, enduring a uniform solution of turmeric in the solvent. Simultaneously, a second solution was prepared by additional 20 milligrams of beta-glucan and vitamin concentrate to 100 milliliters of distilled water. This solution was stirred off at 140 rpm at a controlled temperature of 20 degrees Celsius for 90 minutes, promoting the complete dissolution of the bioactive components in the water. Once both solutions were obtained, they were mixed under constant agitation at room temperature for 48 hours to facilitate the interaction and formation of the particles. Subsequently, the product was subject to a distillation process for 4 hours, which promoted the chemical reaction necessary for encapsulation of turmeric in beta-glucano and the introduction of the vitamins. After distillation, the solvent was evaporated using a rotary evaporation, resulting in a viscous solution with a characteristic yellow color. Finally, the sample was centrifuged at 3000 rpm for 30 minutes, removing the non-encapsulated free turmeric. Continued with the characterization. The first, ultraviolet visible spectroscopy. The presence of curcumin in its bioactive form within the nanoparticles was confirmed using UV spectroscopy, a technique that allowed the analyzing of molecular interaction between curcumin and additional components such as beta-glucan and vitamin C, D3, and zinc. This analysis was conducted using a UV spectrophotometer. The second characterization is Fourier transform infrared spectroscopy, or FTR. The incorporation of beta-glucan, vitamins, and zinc was confirmed through FTR analysis. This analysis was conducted using a Nicolet IS-50 infrared spectrophotometer from Thermo Scientific, employing the ATR mode with 32 scans over a wave number range of 4,000 to 400 centimeters. Finally, the third characterization is scanning electron microscopy, or SEM. The surface methodology and nanoparticle size of nanocurcumin was determined using scanning electron microscopy, or SEM, analyzing, employing a high-resolution HR-SEM microscope brand Auriga.
Okay, moving on to the results. The analysis of the UV-based spectrum of turmeric nanoparticles loaded with beta-glucan and vitamin C, D3, and zinc shows key characteristics reflecting the interaction of these components with curcumin and their effect on optical properties. In the spectrum, shows us a characteristic absorption peak around 350-360 nanometers. This peak is primarily attributed to the pp electronic transitions between the aromatic system of the turmeric nanoparticles, the main active compound in turmeric. Also, a decrease in absorption around 370 nanometers is observed. This indicates that the presence of the beta-glucan and vitamins is slightly altering the position and intensity of the peak due to molecular interactions. Additionally, the decrease in absorptions at longer wavelengths may be related to the size of the nanoparticles and their ability to scatter light, a typical phenomenon in nanostructure systems. This behavior is consistent with the literature, which also reported that the functionalization of curcumin nanoparticles with compounds such as beta-glucan and vitamins enhance their effectiveness in healthy applications. Okay, now we have the spectrum corresponding to the turmeric nanoparticles. First, a band at 3311 was observed, attributed to the vibration of hydroxyl groups, indicating the presence of bonds related to the surface functionalization of the nanoparticles. Additionally, a signal at 2923 was recorded, characteristic of aliphatic stretching vibrations, which reinforces the presence of organic components in the structure. The signals at 1150 and 995 are attributed to the vibrations of carbon-oxygen-carbon and carbon-oxygen bonds, respectively, representing the interaction present in the curcuminoid compound. Finally, a band at 1644 was identified, corresponding to a vibration of the carbonyl group, a key signal related to the chemical structure of the curcumin at the nanometric scale, in accordance with the reported by different investigations. The SEM spectrographs were recorded at 5,000 magnifications. According to SEM analysis, the particles exhibit a semi-spherical morphology, which is consistent with the findings reported in the scientific literature. Consequently, it is inferred that the particle size corresponds to the nanometric scale. Well, here is our final product. The samples exhibit a characteristic yellow coloration in solution containing turmeric nanoparticles, consistent with the reported by scientific literature. Additionally, a particle agglomeration is observed at the bottom of the container, suggesting the need for further optimization of the synthesis methodology to exchange the nanoparticles' stability. In conclusion, the synthesis of turmeric nanoparticles loaded with beta-glucane and vitamin C, D3, and zinc was successfully carried out, as confirmed by the results obtained by FTIR, UV-Vis, and SEM analysis. Although further studies such as cytotoxicity assays are required to fully analyze their bioavailability, the results presented in this work provide a solid basis to consider turmeric nanoparticles as a promising option in the field of food supplements. And that will be all from our side. Thank you very much for your attention.